Hey everyone, ever stop and wonder how our digital devices actually connect with the physical world? How does your phone know which way is up? Or how does a massive bridge know it's feeling a little stressed? Well, there's a kind of magic ingredient behind all of this, an unsung hero. And today, we're going to pull back the curtain on it. It's called the transducer.
I mean, really think about it for a second. Your digital scale, it's just a piece of plastic and some metal, right? A microphone is just this tiny little component. There's no obvious magic going on. And yet somehow, they take real-world physical things, like the force of your weight or the vibrations of your voice, and they translate them into a language that our computers can actually understand. So what's the secret? How do they pull it off?
Well, the answer is this little device right here, the transducer. Put simply, it's a translator. That's its whole job. It takes one form of energy, say the mechanical pressure from your feet on that scale, and it converts it into a totally different form, usually a clean, predictable electrical signal that a tiny computer chip can read and make sense of.
A perfect example we use every single day is a microphone and a loudspeaker. A microphone is a classic transducer. It captures the physical energy of sound waves in the air and turns them into an electrical signal. And then a loudspeaker does the complete opposite. It's what's called an inverse transducer. It takes that electrical signal and turns it right back into sound waves we can hear. They're just two sides of the same coin, and both are absolutely essential for how we communicate.
Okay, but not all transducers are built the same way. They come in all shapes and sizes, but for now, let's just focus on one really key difference, one that changes everything about how an engineer might use them.
On one side, you've got active transducers. Think of these as self-sufficient. They generate their own electrical output. A solar panel is the perfect example. Sunlight hits it, and boom, it creates electricity all by itself. No batteries needed. Then, on the other side, you have passive transducers. Now, these guys need a little boost. They need an external power source to even work. Their trick is to take that power and then change one of its properties, like its resistance. And that distinction is a really big deal in engineering design.
And it's one of those passive transducers that we're going to zoom in on today, the strain gauge. It might be tiny, but this little device is honestly one of the most important sensors in all of modern engineering.
So this is what it looks like. It doesn't look like much, does it? It's basically just a flexible little pad with a super thin, really precise pattern of metal foil on it, kind of like a tiny, squiggly racetrack. But the magic here isn't in what it looks like. It's all about how that little metal track behaves when you put it under a little pressure.
And the whole idea behind it is actually based on a really simple bit of physics. If you take any metal wire and you stretch it, it just gets harder for electricity to flow through it. Its resistance goes up. If you squeeze it, the opposite happens. That's it. That's the secret.
So let's picture this. You take a strain gauge and you glue it onto a metal beam. Now when that beam bends or stretches, even a tiny amount, the gauge that's stuck to it has to stretch right along with it. And that tension pulls on that tiny metal foil, making it physically longer and just a little bit thinner.
And here's where it all comes together. As that little wire gets longer and thinner, its electrical resistance goes up. But because these gauges are made with such incredible precision, that change in resistance isn't random at all. It is directly proportional to exactly how much the material has stretched. And just like that, we have successfully translated a physical stretch, or what engineers call strain, into an electrical signal that we can actually measure.
Okay, so we know its resistance changes, but how sensitive is it, really? Like, how much does the resistance change for just a microscopic amount of stretch? Well, engineers needed a way to put a number on that, and they call it the gauge factor.
Now, don't let the math on screen scare you. The concept is what really matters here. The gauge factor, which is that K in the formula, is really just the language engineers use to talk about how sensitive a particular strain gauge is. It's just a ratio of how much the resistance changes compared to how much the length changes.
So what's a typical number? Well, for a very common material, an alloy called constantin, the gauge factor is usually right around 2.0. And they use that alloy because its resistance doesn't change much with temperature, which is super important for getting accurate readings. But what does a number like 2.0 actually tell us?
It's actually pretty simple. A higher gauge factor is better. That's the bottom line. It means you get a bigger, louder, more obvious change in resistance for the exact same amount of stretch. And a bigger signal is always easier for our electronics to pick up and measure accurately, which is exactly what we're after. All right, so we've just gone super deep on how one tiny sensor works. You might be thinking, okay, but why does this one little thing matter so much? Well, it's because this incredibly simple principle is the foundation for how we sense force, pressure, and movement all around us.
It turns out strain gauges are the secret ingredient inside so many other sensors. They're what's really inside your digital scale, usually packaged up in something called a load cell. They're used to measure the torque on an engine shaft, the pressure inside a tank, even the tiny accelerations that your phone uses to know which way you're holding it. They're absolutely critical for testing the health of everything from bridges and airplanes to giant industrial machines.
You can almost think of them as the nervous system for all of our modern technology. Just like the nerves in your body can feel pressure and movement, these tiny little transducers are constantly sensing the physical forces that are acting on our machines and our structures, giving them the critical feedback that makes so much of our world actually work.
So, the next time you step on a scale, or even just pick up your phone, take a second to think about those invisible translators working away in there. These tiny little marvels of engineering are silently, constantly converting the physical world into the digital data that shapes our lives. It really makes you wonder, doesn't it? How many of these invisible translators are sensing your world right now?